grounding conductor, also known as a grounding electrode conductor or GEC, connects the electrical system to ground, providing a low impedance path for fault currents to flow back to the source. A grounding electrode conductor is a specific type of grounding conductor that connects the GEC to the grounding electrode system. A bonding conductor, on the other hand, connects non-current carrying metal parts such as enclosures, frames, and raceways to the grounding system, equalizing their electrical potential and preventing electrical shocks. The GEC is the primary grounding conductor for the electrical system. It provides a path for fault currents to flow back to the source, reducing the risk of electrical shock and damage to equipment. The term grounding conductor is used in Article 250 to refer to both the GEC, which connects the electrical system to ground, and bonding conductors, which connect non-current carrying parts to ground. This can be confusing, as bonding conductors are not technically grounding conductors in the strict sense. However, the National Electrical Code uses the term grounding conductor to emphasize the importance of these connections in providing electrical safety. While both the GEC and bonding conductors connect to the grounding system, they serve different purposes. The GEC carries fault currents back to the source, providing electrical safety. The bonding conductor equalizes the electrical potential of non-current carrying parts, preventing electrical shocks. The 2008 National Electrical Code did not make significant changes to Article 250 regarding the definition or use of grounding and bonding conductors. However, it did clarify some language and provide additional guidance on specific applications. While the use of the term grounding conductor in Article 250 can be confusing, it is important to understand the distinction between the GEC, which is a true grounding conductor, and bonding conductors, which connect non-current carrying parts to ground. Both are essential for electrical safety, and the National Electrical Code uses the term grounding conductor to emphasize their importance. To further clarify the roles of grounding and bonding conductors, let's delve into some specific aspects of their application and requirements. The grounding electrode conductor, or GEC, is sized according to National Electrical Code Table 250.66, based on the size of the ungrounded service entrance conductors. This table provides guidance on selecting the appropriate size of the GEC to ensure it can effectively carry fault currents back to the source. The GEC must be connected to a grounding electrode, which can be a ground rod, a ground plate, a metal underground water pipe, or a concrete encased electrode, also known as a U for ground. The type of grounding electrode used depends on the specific site conditions and requirements. Bonding conductors are used to connect non-current carrying metal parts to the grounding system. This includes metal enclosures, equipment frames, metal raceways, and other metallic components that could become energized in the event of a fault. The purpose of bonding is to create a low impedance path for fault currents to flow back to the source, which helps to quickly trip the overcurrent protective device, such as a circuit breaker or fuse, and clear the fault. Bonding conductors are sized according to National Electrical Code Table 250.102, which is based on the size of the overcurrent protected device protecting the circuit. This table ensures that the bonding conductors are large enough to safely carry the available fault current. There are different types of bonding conductors, including equipment grounding conductors, which run with the circuit conductors, and supply-side bonding jumpers, which connect the grounded conductor to the equipment grounding conductor at the service equipment. Each type of bonding conductor has specific requirements and applications. It is important to note that the grounding and bonding system must be properly installed and maintained to ensure its effectiveness. This includes making sure that all connections are tight and corrosion-free, and that the conductors are properly protected from physical damage. Regular inspections and testing of the grounding and bonding system can help to identify and correct any potential problems before they become a safety hazard. In addition to the basic requirements for grounding and bonding, there are also some specific rules that apply to certain types of equipment and installations. For example, Article 547 of the National Electrical Code covers the requirements for agricultural buildings, which often have unique grounding and bonding challenges due to the presence of livestock and corrosive environments. Article 517 covers the requirements for healthcare facilities, which have stringent grounding and bonding requirements to protect patients and staff from electrical shock hazards. Article 500 through 516 cover the requirements for hazardous locations, such as those where flammable liquids or gases are present, which require special grounding and bonding techniques to prevent explosions and fires. Understanding the specific grounding and bonding requirements for different types of equipment and installations is essential for ensuring electrical safety. Furthermore, it's crucial to understand the concept of impedance in the grounding and bonding system. Impedance is the opposition to the flow of alternating current and is measured in ohms. A low impedance grounding path is essential for quickly clearing ground faults and minimizing the voltage rise on non-current carrying metal parts. A high impedance grounding path, on the other hand, can slow down the fault clearing process and increase the risk of electrical shock. Several factors can affect the impedance of the grounding and bonding system, including the length and size of the conductors, the quality of the connections, and the presence of any corrosion or damage. To minimize impedance, it's important to use conductors that are sized appropriately, make sure that all connections are tight and corrosion-free, and protect the conductors from physical damage. Additionally, it's important to avoid creating any unnecessary loops or bends in the conductors, as these can increase impedance. Ground fault circuit interrupters, or GFCIs, are an important part of the electrical safety system. GFCIs are designed to detect ground faults, which occur when current leaks from a circuit to ground. When a GFCI detects a ground fault, it quickly trips the circuit, interrupting the flow of electricity and preventing electrical shock. GFCIs are required in many locations, including bathrooms, kitchens, and outdoor areas, where there is a high risk of electrical shock. They are an essential safety device that can help to protect people from serious injury or death. Surge protective devices, or SPDs, are another important part of the electrical safety system. SPD are designed to protect electrical equipment from voltage surges, which are sudden increases in voltage that can damage or destroy sensitive electronic components. Voltage surges can be caused by lightning strikes, power outages, or other electrical disturbances. SPD work by diverting the surge current to ground, preventing it from reaching the protected equipment. SPD are available in a variety of types and sizes, and they can be installed at the service entrance, at branch panels, or at individual equipment locations. Regular testing and maintenance of SPD is important to ensure that they are functioning properly and providing adequate protection. Moreover, it is beneficial to understand the role of the grounded conductor, often referred to as the neutral conductor, in relation to the grounding and bonding system. The grounded conductor is intentionally connected to ground at the service entrance, creating a reference point for the electrical system. This connection helps to stabilize the voltage and provide a path for fault currents to flow back to the source. The grounded conductor is typically identified by its white or grey color, and it is important to distinguish it from the equipment grounding conductor, which is typically green or bare. The grounded conductor should never be connected to the equipment grounding conductor downstream of a service entrance, as this can create a parallel path for neutral current and cause nuisance tripping of GFCIs. Another important aspect of grounding and bonding is the concept of equipotential bonding. Equipotential bonding involves connecting all metal parts within a specific area to create a common electrical potential. This helps to prevent voltage differences from developing between different metal parts, which can reduce the risk of electrical shock. Equipotential bonding is commonly used in swimming pools, spas, and other wet locations, where the risk of electrical shock is higher. The National Electrical Code provides specific requirements for equipotential bonding in these types of installations. It is also essential to be aware of the potential hazards associated with improper grounding and bonding. Improper grounding and bonding can create a variety of safety hazards, including electrical shock, fire, and equipment damage. Electrical shock can occur when a person comes into contact with an energized metal part that is not properly grounded. Fire can occur when fault currents flow through undersized conductors or through flammable materials. Equipment damage can occur when voltage surges or ground faults damage sensitive electronic components. To avoid these hazards, it is essential to follow all applicable codes and standards, use qualified electrical contractors, and regularly inspect and maintain the grounding and bonding system. Furthermore, understanding the terminology used in the National Electrical Code is crucial for proper grounding and bonding. The National Electrical Code uses specific terms to describe different types of grounding and bonding conductors, connections, and equipment. It is important to understand these terms to properly interpret and apply the code requirements. Some common terms include grounding electrode conductor, equipment grounding conductor, bonding jumper, main bonding jumper, system bonding jumper, and supply side bonding jumper. Each of these terms has a specific meaning and application. In addition to understanding the terminology, it is also important to be familiar with the relevant articles and sections of the National Electrical Code. Article 250 covers the general requirements for grounding and bonding. Other articles cover specific requirements for different types of equipment and installations. It is important to consult these articles to ensure that the grounding and bonding system meets all applicable requirements. Staying up to date with the latest edition of the National Electrical Code is also essential. The National Electrical Code is updated every 3 years, and each edition includes revisions and additions to the grounding and bonding requirements. It is important to be aware of these changes to ensure that the grounding and bonding system meets the latest standards. Continuing education and training are also valuable for staying up to date with the latest grounding and bonding practices. There are many resources available for electricians and other electrical professionals, including courses, seminars, and online training programs. These resources can help to improve your knowledge and skills in grounding and bonding. Finally, it is important to remember that grounding and bonding is a critical aspect of electrical safety. A properly designed, installed, and maintained grounding and bonding system can help to protect people from electrical shock, prevent fires, and protect equipment from damage. By understanding the principles and practices of grounding and bonding, you can help to ensure the safety of yourself and others. Always consult with a qualified electrical contractor for any electrical work or modifications to your electrical system. Do not attempt to perform electrical work yourself unless you are properly trained and qualified. Electricity can be dangerous, and it is important to take all necessary precautions to prevent accidents. Remember that the grounding electrode conductor connects the electrical system to earth, providing a path for fault currents to return to the source. Bonding conductors connect non-current carrying metal parts to create a low impedance path for fault currents, minimizing the risk of electrical shock. Ground fault circuit interrupters provide additional protection by detecting ground faults and quickly interrupting the circuit. Surge protective devices protect equipment from voltage surges. Equipotential bonding creates a common electrical potential in specific areas, reducing the risk of electrical shock. Proper grounding and bonding is essential for electrical safety. Always follow the National Electrical Code and consult with a qualified electrical contractor for any electrical work.